Now, before I talk about the single-phase transformers, if you do remember in the last lecture, video lecture, I talked about the electromagnetism, and I was keep repeating that it is a DC current. And we do understand what's the difference between DC and AC, and what complexity is involved in alternative currents. RMS values, average values, peak-to-peak values, and its response to the frequency, the time period, etc. But I really want to repeat the fundamentals, the behavior of an inductor when you supply a pure DC current. So we are going to go step by step. So the first, you have a simple coil, and each coil has a particular value of resistance. Now what happens when you supply a current, a DC current? Well, of course you would say probably that it stores the energy in terms of electromagnetic fields. So as you know that when a current flows through a conductor, it produces a constant magnetic field surrounded by it. It can be acted like an electromagnet or solenoid. But here, in this learning outcome, our interest is to understand the alternative currents, a time-changing magnetic fields. With a pure DC supply, the inductor behaves differently or like alternative currents at the very start when you switch on and at the very end when you switch off the circuit. Now you have already seen the transient response curves for the RL circuit in a DC, in electrical principles DC module, when it has exponential rise and decay behavior for charging and discharging. Now that exponential rise is a change in current, and when you switch off, it's a change in current and an exponential decay method. Now what happens at that particular moment? That's what we are interested in. There's something interesting going on when you supply a pure DC current at the very start and at the very end. That's called self-inductance. And we don't talk about self-inductance when we talk about the DC. So what is self-inductance? Well, self-inductance means an ability for a device or a coil that induces the voltage in it, that generates the voltage because of the change of current. And we can summarize this phenomena in two equations, and those two equations are very famous, and that appreciates the Faraday's law of electromagnetic induction. And what Faraday said, that the induced EMF, the voltage generated in the coil, is dependent on the inductance of the coil or number of turns of the coil, but more importantly, it is dependent on the rate of change of current with respect to time. So for example, if you are supplying a DC, there is no change of current with respect to time like in the case of alternative current. So what happens? There is zero induced EMF. But when you look at the charging and discharging curves of an inductor when you supply a pure DC, there is a change of current at the very start and at the very end when you switch on and switch off respectively. And that's the phenomena was invented by or discovered by Michael Faraday more than 100 years ago. So the equation for the induced EMF is E is equals to minus L, which is the inductance, times the di by dt, which is the differential equation. Basically what it means is the rate of change of current with respect to time. But as you know from our last learning outcome 4, that we know when a current flows through a conductor, it produces the magnetic field, and magnetic field has a unit Weber, can be represented as a flux, phi, Greek letter. So basically the current and the flux are proportional, as you already hopefully know when we distinguish the electric and magnetic circuits. So di by dt can be said as a d phi by dt, rate of change of magnetic flux with respect to time. Now, I already talked about the definition of self-inductance, and it's a very important concept in the transformer. That means whenever there is a change of current, there will be a self-inductance in any way. So self-inductance is an ability of a machine, of a device, of a coil to induce, to generate an electromotive force or EMF within itself in response to a change in current or magnetic flux. Now example question. Now this example question is designed to just practice that equation, but what it means that a coil, an inductive coil with a resistance of 60 ohms and having the inductance of 0.25 henries. Of course, we can calculate the impedance and the voltage and the current and etc. as we have learned already in RLC circuits, but in this one we are going to apply the induced EMF equations. It is connected to a 24 volt DC supply, full stop. Now you can assume that nothing would happen, but in the next sentence it says the current flow through the coil gives rise to a flux of 350 microwebers when the circuit is switched off. Like I said, at the start or the end, at the switch on or switch off. When the circuit is switched off, the current reduces to 0 in 1 millisecond. And we can calculate the induced EMF in that particular period of time that we normally ignore. So induced EMF is equals to minus L di by dt, and by simply applying the Ohm's law, since we have the voltage, we have the resistance, so we can calculate the current change, that is 0.4 amperes. We got the inductance already, and we got the change in time, which is 1 millisecond. So 0.25 times 0.4 divided by 1 into 10 to the power minus 3. This gives you 100 volt as an induced EMF. Now you might ask a question, why there is no negative sign? Well, the negative sign indicates that the induced EMF caused by the self-inductance is due to having the direction opposite to the supply voltage. That means that the induced EMF in the coil will always be opposite in direction to the supply voltage, and that's what the negative sign represents. So it is entirely up to you if you want to put the negative sign or not, but it is important to put the negative sign in the equation to demonstrate that you know why there is a negative sign. Now this negative sign also we will be looking into more details in the section of mutual induction later on. And we can also calculate the number of turns on a coil by just having this data. By using the same equation but in a different form, E is equals to minus n times d phi by dt, and by rearranging that equation we can calculate the number of turns as 286. So what this example question shows, that there is an induced EMF going on at the switch off time, and that induced EMF is also proportional to the inductance of the coil, or in other words, number of turns of the coil. That's the important thing to just mention, the purpose for this example question. Now we are about to begin the power transformer. I always try to recommend everybody to start with the inventor, who invented the concept of power transformer that we use in our daily lives. Still today, in high voltage transmission, distribution, utilization, even in the low voltage applications, just like in my last lecture I shown you the example of wireless charging method. Induction heating system, the low voltage substation transformers or pole mounted transformers. What was the benefit of having a transformer in any way? Well, transformer, by its word, that transforms the voltage from one level to another level. And we need to ask the question why. But before we go into details, but I really recommend you to read the Nikola Tesla's patent, which was published in 1897, and you can read his words, his invention for the creation of this transformer that we still rely on. But of course, we need to ask a question: what is a transformer first? You know, what is it, how can we define? Well, is it a transformer? Is it a machine, or is it a equipment? Is it a device? Well, it can be anything. Typically, a transformer, a power transformer, is a machine. Is an electrical circuit or electromagnetic circuit or magnetic circuit. You name it. The way you have to define the transformer, it depends on your perception, it depends on your perspective as well. How are you going to analyze the transformer? So a transformer, for example, typically or traditionally is a machine that changes or steps up or steps down the voltage of the AC system. But now we need to ask a question: why do we need to change the voltage? Why there are so many applications of it? Well, first, if you do remember the active power formula, P is equal to VI cos of theta, transformer does not transform the power. It supplies the same power from the input to the output, considering that each and every machine would have a losses. So it might be a little bit lesser output power in the real case scenario, but in the ideal case scenario, input power will always be equal to the output power. And ideal doesn't exist, but we do practice to make sure we know how to use the equations. So the question relies to our active power equation, P is equal to VI cos of theta, and let's suppose cos of theta is constant or is 1, for example. So if you increase the voltage, you've got to reduce the current in order to transfer the same power. So if you reduce the current, you can reduce the size of the conductors. And if you reduce the size of the conductors, you reduce the losses and the cost of the materials. And that was the war between Thomas Edison and Nikola Tesla more than 120 years ago. That which system was better, DC system or AC system? At the end, AC system is still we are relying on for over 120 years. Now, the second sentence, how the transformer operates, under what principle? Well, the transformer operates on the principle of mutual inductance. We need to look into details what is mutual inductance, number one. And due to that mutual inductance only happen when there is a time changing magnetic field. Now we need to look at the time changing magnetic field as well. So a transformer operates on the principle of mutual inductance due to the time changing magnetic field that induces the voltage in coil 1 of wire 1 on the left hand side if it passes through the secondary coil without touching to each other. There is no electrical contact between it. It's a wireless energy transmission. That's why I talked about the wireless charger in my last lecture. So if I look at this sketch for a coil, and the coil 1, for example, if you supply the alternative current in coil 1, it would have the changing current, and the changing current would have the changing magnetic field. That means in the positive cycle, it would have the north and south poles. In the negative cycle, the poles changes. That's what the time changing magnetic field means. So this time changing magnetic field can actually first will induce the voltage in coil 1, but if it passes, or if the secondary coil or coil 2 places next to it, near to it, not touching to each other electrically, it would cut the flux in the coil 2. It will induce the voltage in coil 2. That's called mutual induction. That's a natural phenomenon. Now we need to look at, like I mentioned, that in the positive cycle, it has a north and south poles, and after 180 degrees of the AC waveform, the poles changes, and this happens constantly. As you know, 50 Hertz is about 20 milliseconds. That means 20 milliseconds is the time period to complete one cycle. So this is being happening after every 10 milliseconds. Now this introduces the concept of pulsating magnetomotive force. Now the pulsating magnetomotive force is, as you know, is dependent on the number of turns and the current flow through it. The reason we use an adjective pulsating because of the time changing current. So the transformer is dependent on pulsating MMF. There are three types of magnetomotive force. One is called static MMF, which what we were dealing with in our last learning outcome, electromagnetism. Everything was static. The pulsating MMF is what we use in transformer. That's the basis of its operation, time-changing magnetic fields or pulsating MMF. There's a third concept called rotating MMF. So in order for us to rotate the rotor of a machine, of a motor or generator, we need to have the rotating forces on the stator, invisible rotating forces, magnetic forces. And that is the basis or the function we need to create in the motors or generators to run the machine, to rotate the machine. What you are looking at on this PowerPoint presentation slide is the imagination that the forces changes after 180 degrees. So the first it will become pointing towards the north pole, upwards and then downwards, and changes after every 10 milliseconds. And what happens, there are two phenomena going on. One is a self-induction and second is a mutual induction. So the EMF induced in coil 2 is due to the mutual inductance, and we need to understand what is mutual inductance. So let's suppose there is a mutual induction, and that mutual induction is dependent on rate of change of current with respect to time in the primary coil or coil 1. What you are looking at is the equation EMF in coil 2. E2 is equals to minus M mutual inductance times the di1 over dt. Now the negative sign indicates that the EMF induced in coil 1 or coil 2 will be opposite in direction to the main supply voltage. And that phenomena was discovered by Lenz, and it becomes a Lenz's law. Now the same equation can be explained in a different way. The EMF induced in second coil or secondary coil is because of the number of turns the second coil has, but also because of the flux linkages in the second coil with respect to time. Means there's a magnetic flux linkages going on, so cutting going on, and the same equation can be represented in a different way. So here we have two equations. One is E2 is equals to minus M times di1 over dt, and second equation is E2 is equals to minus N2 times d phi 2 over dt. Now if we compare these two equations, we can substitute and find out the value of M, which is the interest to know what is mutual inductance. And after doing that, mutual inductance can be represented in a simple equation, which is M is equals to N2 times d phi 2 over di1. So what it means that the mutual inductance in Henrys is dependent on the number of turns of a coil 2 times the change of magnetic flux linkage in coil 2 with respect to the change of current in coil 1. That's what is the mutual inductance, and I have also written that in words as well in case. Now here's a simple mutual inductance example question. It says to determine the following: value of induced EMF in a secondary coil E2 when the current in primary coil changes from 5 amperes to 1 ampere. D is called change. So what would be the change between 5 and 1 ampere? So that would be a 4 amperes DI. Which DI? DI1. And the DT is, because it says 50 milliseconds, so that's your change in time. And the mutual inductance between the coil, so M is given, is 0.5 Henrys. What we have to calculate is the value of the induced EMF based on these parameters. So to calculate the value of induced EMF, E2 is equals to minus M, so there should be a negative sign here in the equation, like I mentioned before. So I apologize, please do consider a negative sign in this equation. And dI1, which is 4 amperes, the change in current in primary coil, and the dt is the change in time, which is given 50 milliseconds. So this gives you induced EMF on that particular moment when the current changes is 40 volts, minus 40 volts or 40 volts. You got to use the negative sign in the equation. Part number B says calculate the number of turns in coil 2 when the flux linking the coil changes from 12 to 2 milliwebers. So 12 to 2 milliwebers. So what is the change between 12 and 2? Is it 10 milliwebers? Or you can simply subtract 12 minus 2, that's 10 milliwebers. So to find out the number of turns in coil 2, N2, we use this mutual induction equation. By rearranging that equation, we got the parameters and we can calculate the number of turns of the secondary coil. It can be applied to practical circuits as well. Part C says calculate the rate of change of flux linking coil 2. Well, the rate of change of flux linking the coil 2, what we are interested in, the d phi by dt, rate of change of flux with respect to time. So we have the equation E2 is equals to minus n times d phi over dt. By rearranging that equation, we can calculate d phi over dt by just dividing 40 with 200. This gives us a value of 0.2 Weber per second. The reason the unit is Weber per second because it is a change of flux which is Webers with respect to time, that's why Weber per second. Now, in this case, what we are interested in, the principle of operation of a single phase transformer, and we have briefly looked at the mutual induction equation, induced EMF equations in the secondary coil. Now what we need to understand is the relationship between the voltage and the number of turns, because as you know that the transformer changes the voltage, so it is important to know how many number of turns we need to achieve the particular voltage. Whether it's going to be step up transformer, that means it will step up the voltage, or it's going to be step down transformer that will reduce the voltage. So let's suppose you have the supply voltage and you have the output voltage, and in between there's a transformer. So we can identify the relationship between the number of turns and the voltages if we know that the flux linkage d phi by dt is constant. And when you construct a transformer, it becomes constant. And by doing that, we can compare both equations. E1 over N1 is equals to d phi over dt, and E2 over N2 is equals to d phi over dt. Since E2 is equals to N2 times d phi over dt. If you do remember the previous one, this equation, E is equals to minus n times d phi over dt. So now it depends on which induced EMF we are talking about. So let's suppose the d phi over dt, which is d phi 2 for example, is constant, then we can compare these two equations here, and it can be assumed that the induced EMF in the primary winding is proportional to the number of turns of the primary winding. Induced EMF in the secondary winding is equal to or proportional to the number of turns of the secondary winding. I want to talk about the difference between the induced voltage and the supply voltage, because supply voltage is the voltage that you supply from the mains power. That's, for example, 240 volts RMS, 50 hertz at the reference angle of 0 degree volts, for example. So you supply that voltage to a transformer, there will be some losses due to the core, due to the windings, resistance, leakage reactance, etc. And then finally it will reach to the primary coil. So when you supply the voltage, it's not going to be like the voltage that you supply will go straight to the primary winding. There will be some losses. So the terminal voltage V1 and E1, which is the induced voltage in primary winding, in the real transformer, in the ideal transformer, they are the same, because that is the topic of our concern, to analyze the ideal transformer, where your terminal voltage V1 and E1 would be equal. But when we study the real transformer, then the V1 and E1 would no longer be equal. So that's something I need to really clarify, because in the next semester when we study the transformers, real transformers, then there will be a similar discussion. So at this moment, we can assume that E1 over E2 is equals to V1 over V2 is equals to N1 over N2. Since the current flow through the conductor and the number of turns both are balanced in the primary and the secondary windings, in other words, the power is equals to V times I. So if it is V1 I1, then V2 I2, we can come up with a relationship which is I2 over I1 is equals to V1 over V2 is equals to N1 over N2. So there are two ways we can relate the current to the number of turns. So one method is here. So primary ampere turns must be equals to the secondary ampere turns if you want to balance the circuit of a transformer. Then by rearranging this equation, it can be said that the I2, the current in the secondary coil, is proportional to the number of turns of primary coil, and the current in the primary coil is proportional to the number of turns to the secondary coil. So by combining this equation and this equation, we can come up with a unified equation. Now this unified equation is a little bit incomplete because, like I mentioned, that we will be analyzing the ideal transformer. This equation is valid to a real transformer and also ideal transformer. But the only difference is you need to say that V1 over V2 is equals to E1 over E2 is equals to N1 over N2 is equals to I2 over I1. In other words, there is no difference in the ideal transformer between the terminal voltage V1 and E1. And the same thing applies, there is no difference between the E2 and the output voltage in the ideal transformer. Now this was all about the equations to understand the relationship between the number of turns and induced EMF, mutual inductance, time-changing magnetic fields. But now we are going to construct a single-phase transformer. Now this will also be relevant to a real transformer, because in order for us to construct the transformer, we got to be realistic, right? So let's start the construction of a transformer. There are two main types of construction. We call it core construction. One is called core type, which is on the right hand side, and that core type has upper yoke, lower yoke, and the limbs, the outer limbs, where we can wind the primary coil and the secondary coil. But as you can see on the right hand side, that there is an air gap, and you do know that the reluctance would be higher if you have a higher air gap. We try to reduce the air gap, and we will be looking at these phenomena more in detail later on. The second type is a shell type, which is more commonly we use, and you will be having a pleasure to construct this transformer next semester in the laboratory in a new module, Electrical Technology. The second type is a shell type, which is on the left hand side, that has a central limbs, outer limbs, upper yoke, lower yoke. And what we do in this type of construction, we can construct a small or lower voltage transformer. It's not relevant or is not useful for high voltage transformer application. Thus we have a different types of construction. But the principle remains the same. The construction principle remains the same. So we are going to construct the single phase transformer now by using the shell type construction method. So let's start. First, if you want to build a transformer, you need two coils. So first coil is a primary. It's a number of turns. We decided to have that first number of turns on the central limb, wound around the central limb. Now the question is why? Why not in the outer limbs? Well, it's because it would be easier to handle the transformer. It would be easier to construct the case, to hold the transformer, but also to improve the flux linkages as well. This type of transformer, as you are looking at the pictorial representation of a shell type transformer, it looks like there is a little bit more air gap here. We try to reduce the air gap as much as possible to reduce the reluctance. So this is the primary winding. Well, this primary winding is made of what? Copper? Copper material. That's the most commonly material we use. But there's one more important detail we need to remember, that it's not only copper. That copper must be insulated with enamel, for example, or any good quality insulation material. It has to be insulated. So we use the word copper wire enamel insulated. Then we need to apply the masking tape. Now the question is why we need to apply the masking tape. Well, it's to protect the winding, to separate or to insulate the primary and secondary winding. That's why we need to apply the masking tape. Like I said, this is the method suitable for low voltage application. For example, if I want to step down the transformer 24 volts to 8 volts, that's a low voltage application, a low voltage type of transformer. where we can use these methods. But in a high voltage application, we've got to use oil, natural ventilation methods, and so many complex methods to cool it down, to separate from the primary and secondary winding, to have a paper insulation, whether it's a cylindrical or disc type construction. That is a topic of interest in the high voltage application. But now we need a secondary coil. Now the secondary coil must be top on the primary coil. That means we are reducing the air gap between the primary and the secondary coil. That's the number one reason, and the probably only reason we need to apply the primary winding and secondary winding on top of each other. Second, the use of masking tape and insulated copper conductors is to make sure that it should not create any electrical contact, because that would be a disaster. That would be a short circuit of a transformer. Sometimes people get confused that the primary and the secondary windings are electrically connected to each other. That's not true. It's a short circuit. So we have to insulate the primary and secondary winding to a level even when it heats up, because when a current flows through a conductor, it will produce the I square R loss. It will produce the heating effect. So we have to protect the primary and secondary winding to avoid the catastrophic short circuit. And then we have to apply the masking tape again to just make sure that primary and secondary winding are intact. They should not move. Now, there are more questions. Let's start with a number of questions that I think you might be asking. So the first question is, windings are made of what? It's made of copper wire. Why? Because it's cheaper. Do you think that the windings should be insulated? Yes. They should be enamel insulated. Why windings are wound on top of each other? To reduce the air gap, to reduce the leakage flux. I need to talk about the leakage flux because I just mentioned it. To reduce the fringing loss. And I will be talking about the fringing loss as well. The third question says why we need a masking tape: to just provide extra protection. If in the case the primary or secondary windings enamel insulation got melted up or some kind of cut up, then it may create a short circuit. So we just apply the masking tape to make sure it's protected. The fourth question that I come up with, which is why we need the core in any way. That's a very good question, by the way. Why we need this all formality? Well, number one, we need a material where we can wound the winding. That's the number one reason. You need a material. Number two, because of the pulsating MMF or pulsating forces, it would create the vibrations. So you need a material that can handle those vibrations. And the third, we need to make sure that the flux linkage, rate of change of flux with respect to time, should not be escaped in the air. We call it leakage flux. Or in other words, to improve the flux linkage between the primary and secondary winding, we have this core that allows a good path. It's like a water pipe that gives a direction to the flux. Please flow within the direction to reduce the losses. Now, as you have already looked at these lines, what these lines means, we call it laminations. But why we need to laminate the core? Well, first of all, we need to know what is lamination. The lamination means you have a piece of material either made of ferromagnetic core, iron, nickel, or highly permeable material, stainless steel. You've got to cut that material into as many slices as possible, and each slice must be insulated to each other. And now the question is why? To reduce the eddy current loss. What is eddy current loss then? And that is the topic of our interest in the next upcoming slides. But briefly, I have written the solution, the answers of those questions, and that's the strategy I'm using to make sure I ask questions to myself and answer at the same time to improve the critical reasoning skills. Now, obviously, you will be thinking that there are so many losses going on here. The leakage flux, the fringing loss, the eddy current loss, the I2R losses, and the material that it has to be made of is stainless steel, highly permeable, and there's a new term which is called hysteresis loss. So I need to talk about these things. So this transformer is not perfect because of the losses in a single phase transformer. Now we will be doing calculations more in detail in next semester, but I want to briefly mention, by taking advantage of this time, that we know what we are doing. I just want to mention that in the ideal transformer, none of these losses occur. It's like a 100% efficient engine. Nowhere in the world is a 100% efficient engine. You might achieve 98%, 99%, or not 100%, according to laws of conservation of energy. So the first loss we need to look after, which is the I2R loss, copper loss, and that is due to the copper, the conductor's material, which has a particular value of resistance, and that creates heat. So that's the number one loss, straightforward. The second loss is called hysteresis loss. I was talking about permeability last week. I was saying how easy it is for a material to establish the magnetic field and how easy it is for material to demagnetize the magnetic field or de-establish the magnetic field. Permeability. We have also looked at the relationship between permeability and B and H. We call it a BH curve. And that BH curve is relevant to hysteresis loss. Because if you have an iron core that might store the magnetic characteristics within it when you supply an alternative current, and that storage would create the opposition within it, and the result is heat power loss. So hysteresis losses are associated or caused because of the arrangement and rearrangement of the magnetic domains in the material, in the core of a material, not in the winding, in the core, during each half cycle of the alternative current. They are complex, nonlinear function of the voltage applied to the transformer, and they cause harmonics because of the storage, tiny storage of the magnetic fields in the core of the material. It actually manipulates with the supply voltage, and we call it distortion to the supply frequency. We have a first harmonic, third harmonic, fifth harmonic, 7th, 9th, the odd harmonics, and we also have even harmonics. That will lead us to go to the Fourier series analysis of a AC waveform, which I hope I would have a pleasure in next semester. I would be able to explain the Fourier series of a hysteresis loop. But we will be looking at the hysteresis loop, how it looks like, what it is. So we will be looking into details later in this lecture slide. But this is just a quick explanation about what is hysteresis loss. So hysteresis power loss is proportional to the frequency of the supply voltage. That means if you have a transformer in the United Kingdom that we have 50 Hertz supply frequency, you might have the less hysteresis loss in that the same machine compared to the same machine you use in the United States that has a 60 Hertz supply frequency. So that's the frequency is also important to use the machines wherever you want to use. The third loss is the eddy currents. I just mentioned that we have to cut the core into many pieces, slices, and laminate each slice to each other, and each slice must be insulated to each other to reduce the circulating current. Now what is circulating current? Now remember, this alternative current is not straightforward. When I talked about the self-inductance induced EMF, so whenever alternative current or pulsating MMF flows through the winding, through the material, it would have its own induced EMF. So basically, the eddy current can be defined as a current that flows from the material, the core of a material, and because of the self-inductance, because it induces the voltage within it. And the eddy current power losses are inversely proportional to the square of the lamination. More laminations we would have, lesser the eddy current losses we would have. The fourth one that I mentioned is the leakage flux, the flux which escapes from the core winding that do not link to the secondary winding, or that is not useful. It's called leakage flux. And the fifth one is fringing loss. Well, fringing is due to the air gap. So like I talked about before, that the core type construction has a more air gap compared to the shell type, and we have to keep the windings as close as possible to reduce the air gap. Is because of the fringing loss. So some of the flux would be lost in the air. So we have to avoid or reduce the fringing loss. We cannot avoid it, but we can reduce it. So now it is time to just look into a little bit details on the losses, and we will be discussing these losses with more details in next module, of course, in the next semester. But of course now, so far, if we can summarize, there are basically three types of losses. One is the I-square-R losses, and second, the iron or core losses. That consists of hysteresis and eddy current losses. And the third is a leakage flux, where also fringing comes into effect as well. Now, copper losses or I-square-R losses, they are simply the representation of the heating effect in the motors or generators or transformers. And one of the easier possible way to detect the temperatures of the machines is to use infrared thermography, which we nowadays pretty much relevant to our today's situation, to use infrared thermographic cameras to detect temperature of people, for example. It has a wider application, but it also has the lower accuracy as well. It depends on the quality of the camera. The eddy current losses, like I said, that these are the circulating currents, and the end effect, of course, is the resistive heating losses in the core of a machine. They are proportional to the square of the supply voltage to the transformer. In other words, eddy currents are circulating currents produced by the transformer action or mutual inductance in the core of electrical apparatus or machine. In order to reduce the hysteresis losses, eddy current losses, we have to cut the core into many slices and laminate each slice with respect to each other to reduce that circulating current. And this diagram shows that how the circulating current would look like in the core of a transformer. And it can be seen that the main current flow through the core of a transformer is the supply voltage or supply alternative current, but the eddy current that flows is opposite in direction, is the fundamental principle of the self-inductance or self-induced EMF in the core would have opposite direction to the supply voltage. And by cutting that the same core, we can reduce the circulating parts, as it can be seen on the right hand side compared to the left hand side of the solid core. I just want to mention that there are so many applications of eddy current losses as well. It's not only a losses, but there are actually devices that you can search on YouTube. I have just given you one YouTube link that demonstrates how eddy currents melt a black tape on a copper flat bar due to the heat generated. Now, in the transformers, it is a loss, but people also use the same phenomena for a number of other applications. Well, the easiest possible solution to reduce the circulating current is to reduce the number of circulating parts, and that can be done by slicing the core into as many pieces as possible and laminating, insulating each slice with respect to each other. That would improve the resistance. Now here we have an example question. For example, if an EMF of 5 volt induced in a solid core of a machine, and that is, for example, is unlaminated, it's a solid core, and let's suppose that solid core has a resistance of 1 ohms, and let's suppose it has the eddy current, induced current of 5 ampere flow through it. Now, if we do apply the fundamental I square R power equation to calculate the power loss, that would be straightforward. P is equal to I square times R. It gives you the power loss of 25 watts. Now, if the same dimension, if I cut that the same solid core into laminations, let's suppose 5 laminations, each lamination must be insulated, which means, let's suppose, it increases the resistance, but also it divides the voltage because they are connected in series. So if you divide the voltage induced in each lamination, but also you increase the resistance by insulating each lamination, each slice with respect to each other, that means you will have the induced voltage of 1 volt, for example, based on the 5 lamination, and the resistance would increase 5 times because of the 5, let's suppose 5 ohms. And if we calculate the current by applying the Ohm's law, it gives us 0.2 amperes. And if we apply the same power loss equation, I square R, the power loss would be reduced from 25 to 0.2 watts. Now you might be thinking that, it doesn't make any difference, it's a small power loss, 25 watts. But when we talk about 1000 watt power transformer or 1 megawatt transformer, then it would make a huge difference in terms of the cost savings or power loss savings that can be consumed by the consumers. They can be charged or standard tariff. So that would be the power loss of each, for example, 0.2 for each lamination. But if you do add up those individual power losses because of the individual voltages and the resistances, that would be the power loss of 1 watt. So that's a total reduction from 25 watts to 1 watt. In other words, the core power loss is proportional to the square of the cross-sectional area. It makes a huge difference when you increase the cross-sectional area for certain reasons, like to reduce the vibration in the transformer, to improve the insulation, to improve the flux linkages. You got to consider the resistance of the core. You got to consider the eddy current as well. But that, of course, is dependent on the resistivity of the material as well. Now, the second, again, the core power loss, the second part of the core power loss or iron loss is the hysteresis loss. And I have already discussed about briefly the hysteresis loss, which is the arrangement and rearrangement of the magnetic domains within the core of a transformer or material. We can reduce the hysteresis loss by increasing the permeability of material, and the best so far material we so far used is stainless steel. There are other good materials available in the market, but hysteresis losses we can reduce it. But it can be represented, it can be calculated using oscilloscope, and we will be doing this when we construct the transformer next semester. And we will be able to see the hysteresis loop of a transformer. And that's how it would look like, the complex hysteresis loop. We call it BH curve. That's what I mentioned in my last lecture, BH curve. Now you do know what is B and what is H. B is the magnetic flux density, H is the magnetizing force or magnetic field strength. And both are interdependent. So let's begin by understanding how the hysteresis loop is complex and why it is that. So let's suppose you are supplying a pure sinusoidal AC supply. And let's focus on first positive cycle. So what happens when you supply an alternative current to a coil? The core magnetizes and it reaches to the saturation point, the maximum point, and then it falls back to the zero. But it will never be able to demagnetize the core of a material because it would store certain elements of magnetism in the material. So what we are looking at, let's suppose we are starting from 0 degree sinusoidal AC supply and the core has a nonlinear behavior. This is the saturation point or peak point at 90 degree of the AC supply voltage. And then it goes back to the 180 degree, but you would expect the graph goes to 0, but it would never go to 0 because it would stay at certain magnetic flux density. We call it residual flux density. Residual means something which is left in the core. And when after 180 degree, it would start its second cycle, and it will go like this. The peak, which is 270 degree, and goes back to 360 degree, but it will never achieve its 0 point because of the residual flux density on the vertical axis. So vertical is magnetic flux density, horizontal is magnetic field strength. Now we have a terminology. So terminology on the vertical axis, this particular point is called residual flux density. The energy required to demagnetize that stored magnetic energy or field is called coercive force, which can be represented as a horizontal, that particular point. And that force is basically consumes power. It creates harmonics. And this is the complete hysteresis loop. So you will always have a transformer with a particular loop, and it would have the particular area of the hysteresis loop. So these are the just definition of what is residual flux density or remnant flux density. We use the both words, and we will be looking at these same words in more specifically in next semester. So a magnetic field which is left in the core is called residual flux in the core, something which is left. To force this flux to 0, an amount of MMF required is called coercive MMF or coercive force. Now, how can we neutralize the core of a transformer? Well, there are a number of methods being applied, but the simple and the fundamental method is to apply the mechanical shock or extensive heat to the transformer. That would damage the transformer, simple, or could damage the transformer. But these are the, in order to demagnetize the core, you need to apply certain energy, either electrical energy or some mechanical shock forces, etc. Now, hysteresis loop, like I said, that is dependent on the cross-sectional area of the loop. So, the smaller the area, better the core material is. That means higher permeability. And if you have the larger area, that means it has more hysteresis loss. That also means the material has lower permeability, can be improved. Of course, the effects of the hysteresis power loss is the heating effect, harmonics, distortion to the supply frequency. In other words, it will decrease the efficiency of the machine. And what is efficiency? Well, efficiency is the output power over input power. So you supply the input power, your output power will be a little bit reduced because of the losses. But if you are talking about the ideal transformer, that's not the case. In the ideal transformer, there are no losses. So that's the topic of interest when we want to apply the fundamental equations of the voltages and number of turns to practice. But there are, of course, research papers on this, how to reduce the hysteresis losses. And this is one of the example paper in Nature, published in 2004, as a number of materials being developed so far to reduce the hysteresis losses. So it's a huge area where research is going on. And of course, the leakage flux is again with the flux which does not link to the winding, that escapes out from the winding. That's what is called leakage flux, and this is what this slide shows. Now it's time for a little bit practice example questions. I set up the example questions as a multiple choice or true and false, or just to answer the question, for example. So question number 1, it says, what are the 2 typical types of core construction of a single phase transformer? And this goes back to our first few slides for the construction of a transformer. And there are 2 types of construction, typically what we covered in this lecture is the core type and the shell type construction. And let's look at the other question. The core of the single phase transformer is typically made of a silicon steel material. Why? Because it should have a higher permeability. To reduce which of the following loss that associated with the arrangement and rearrangement of the magnetic domains in the core during each half cycle of AC. So which loss is that one? Is it a heating loss? Well, heating is the effect. Eddy current is the circulating current. That has nothing to do with the arrangement and rearrangement of the magnetic domains. We haven't talked about the Faraday current. So it must be a hysteresis loss. Question number 3. A single phase transformer is an electrical machine that would operate using the pulsating MMF. Is it true or false? Or neither true or false? But of course, what we so far learned, there are 3 types of MMF: static MMF, pulsating MMF, and rotating MMF. So the transformer relies on a pulsating MMF, so it's true. Question number 4. The hysteresis power loss occurs with each cycle of the supply AC voltage and is directly proportional to what? To the frequency. And then finally the question number 5 says the eddy currents are circulating currents produced by transformer action or mutual inductance in the core, slicing the core into many laminations and insulating one from each other will reduce the magnitude of the eddy current by providing smaller paths for its job. Eddy current power loss is inversely proportional to the square of what? Not the primary winding. It has nothing to do with the primary winding. Certainly not to do with the secondary winding. It has to do with the core lamination. So C is the answer, and D is times to heat up the core doesn't make sense, of course. So C is the straightforward answer. Now here we are. I would like to go into detail to construct the single phase transformer, to perform open and short circuit testing in the next semester, where we would have more time, and which the module is specially designed for the transformers and the motors. But this is how the realistic equivalent electrical circuit would look like for the transformer, that we have just looked at how it was constructed. That consists of the losses. So what we are looking at, the magnetizing current, magnetizing reactance, core loss resistance, core loss current, no load current, input current, the resistance of the primary winding, the leakage reactance of the primary winding, the resistance of the secondary winding, the leakage reactance of the secondary winding, secondary terminal voltage, secondary terminal current. Induced EMF would be different to the V2 because of the losses. That's the case with a realistic single phase transformer. But like I said, we will not be studying this in this semester, but it is good to know, to have the fundamentals in this electrical principles AC module. Our topic of interest at the moment, or in this lecture, is ideal transformer. Why? Because we want to practice the complex algebra. We want to practice the equations, the fundamental equations for the voltage, number of turns, and the current before we start the realistic transformer next semester. So what is the principle of operation of an ideal transformer? Well, it's simple. It would work on the principle of mutual inductance and time changing magnetic field. it will induce the voltage in the secondary winding, but there will be no losses. There is no hysteresis loss, there is no eddy current loss, there is no fringing, there is no leakage flux. So the characteristics of an ideal transformer is that it is 100% efficient. And the reason we are dealing with this type of transformer in this semester at level 4 is to practice. Of course, I just want to reiterate to make sure that the realistic transformer would be studied in electrical technology module. So now let's look at the equations. So the equations remains the same as we discuss about the induced EMF and input power or output power, both are equal, so we can compare. P is equals to V1 I1 is equals to V2 I2. We can step up the voltage, step down the current, and vice versa. So finally we will have the equation like this. Now this goes back to our initial point when we talked about the mutual inductance and the unified equations. When I mentioned at the very start that the induced EMF is equals to the terminal voltage in the ideal transformer. In the realistic transformer, it's not the case. So now in this semester, we will be focusing on these equations. So there are 3 equations within it. V1 over V2 is equals to N1 over N2 is equals to I2 over I1. And now it's time for a tutorial example question that I'm supposed to be solving on whiteboard. So I will be solving this question with you in a way, trying my best that would not compromise your learning. So what we are looking at in this tutorial example question, we have the input voltage 500 volts. And we assume that there is no resistance here, so it's a pure ideal transformer, obvious from the circuit diagram, because there are no resistances, there are no core loss components, so which means that the input voltage V1 500 is the same as the induced voltage here. Right, there's an input current flowing through the primary coil, and these 2 lines represent the core of a transformer. If there are no 2 lines, which means it's air-core transformer. Air-core transformer, which means it's just the windings, 2 windings in between there's the air. If the windings are wound on the core, that means it's core type construction. So you have the secondary current I2 and V2, and the load is connected as a resistance. Now here is the twist. We can apply the equations like this in a simple steady state way or in a complex way. So this is the application of complex algebra as well. But we have to distinguish. If I give you a pure resistance 20 ohms, and if I give you 500 volts with no angles to mention, there is no complex current flow through it, it's all simple. That means our example question does not involve any complex algebra like a polar form, rectangular form of the current, voltages and impedances. There's no concept at the moment in this example question. But that's a concern. We will have to apply our complex algebra to tutorial questions. That is my next section. So the question says if the number of primary and secondary turns are 1250 and 200 respectively, which is N1 is 1250, N2 is 200, calculate the secondary terminal voltage. So which is straightforward. V1 over V2 is equals to N1 over N2. You got N1, you got N2. You got V1, and by rearranging the equation, you can calculate V2. The second part is, if you just want to see the secondary terminal voltage, V1 over V2 is equal to N1 over N2, and by rearranging the equation, we can calculate the V2 terminal voltage 80 volts. It can be seen that the primary voltage was 500, the secondary voltage is 80 volts. So 500 primary, 80 volt secondary. So this is called a step down transformer. If you reduce the voltage, you increase the current. So the second part says calculate the current flow through secondary winding and primary winding. So how can we find out the secondary current and primary current? Well, we know the equation I1 over I2 is equals to N2 over N1, or I2 over I1 is equals to N1 over N2. But here we have two unknown parameters. So what we can do, we can use a simple Ohm's law. In this case, we have the pure resistance 20 ohms. We can use V is equals to IR to find out the secondary current I2, and then by using any of the method, either I2 over I1 is equals to N1 over N2, or I2 over I1 is equals to V1 over V2, which is the same thing here. By rearranging the equation, we can calculate the I1. So here the trick is to use Ohm's law. The part C says calculate the power dissipated by the resistive load, output power. Well, you can use the formula P is equals to VI, P is equals to I square R, or P is equals to V square over R. Any formula you can use, and it should give you the same answer. So in this case, for example, if you say I2 square times R, it gives you 320 watts, and part number D says power drawn from the supply input power. Now you have to use your prediction. Since it is the ideal transformer, the input power must be equal to output power. By some magic, if you come up with a different answer, which means something is wrong in the calculation, because it is all about, at the moment, ideal transformer. So supply power can be calculated as input voltage times input current. Make sure you are consistent whether you can use I2 V2 or V1 I1. In this case, with the power drawn from input, we use V1 times I1, and this gives you 320 watts.